Today we are starting chapter 13, which is on policy gradient methods, which is a pretty big departure from what we've done so far in the book. And all the methods we've considered previously are action value methods of one form or another. And then the action values that we calculate are then used for some form of control, like to improve the policy. And like the cornerstone of part one of the book, which is on tabular methods, is the policy improvement theorem, which provided a way of like iteratively improving some policy. And I have this notebook that summarizes part one of the book, but it's useful to just give a quick recap of how the action value methods work. So, some environment is defined by this probability transition function. And then when you interact with the environment, you are going to go through some trajectory of states. In this case, this is showing like a case of an episodic trajectory where it ends at some point, at some terminal state. And how this trajectory works, like where you end up, these white circles represent states in the environment, will depend on the environment, like how it works, what are the rules of transitions, and also like what actual policy is being followed by the agent. So then, from trajectories like this, we had this goal of calculating some kind of value function from the trajectory. And this was one definition of the discounted return, where we sum along this trajectory, along all the steps, these R values, which are the rewards that you would receive after every step. And those rewards are determined by the environment and how the dynamics of the environment work. And then we defined these sort of two different types of value functions based on the policy. And the actual simple definition of them is just like the state value function is just the expected value of this discounted return from a particular starting state. And then the state action value function, it's exactly the same, except that we also take a particular action initially, whether or not it's the action that the policy would take, right? So that's the only difference between the two types of value functions. And then, we had in this is an example of like a grid world environment. Maybe I have a better example of, yeah. So this is like a grid world environment where this, if you have the random policy like this, what's shown here is the corresponding value function, which we had techniques in part one of the book to calculate these value functions. And it does depend on the discount rate here and other things. But this environment is just useful because you can just directly see what the states are. They're just these different points in the grid. And this sort of concept generalizes to any kind of environment, but then in other environments, instead of it being like a literal grid of states, like the states could be other things, but you can just clearly see here that like the rules of transition are just moving between states. It's just like moving in the rectilinear directions. And then given the policy, you can compute a value function. And all the methods so far, including in part two of the book, where we were doing it with approximation, involved starting with some random policy usually, and then going through iterations. So here, like this is showing after one iteration, you use the value function to improve the policy. And here, this is like after one step of improvement. And then in this case, this whole thing converges after 5 steps. And you can see this is a trivial example. The optimal policy involves moving to this goal state as quickly as possible.
Enough money in the market.
So yeah, this is showing an example of like using the policy improvement theorem to improve the policy. And in the part two of the book, we're dealing with approximations. We're doing all the same things, but now instead of having like a value function like this, where there's a finite state space, we have a value for every state. We had some function with parameters where the parameters control what the values are, but the actual states, like that, there's not this finite number of states. We have to use some other technique, some approximation function to, where the number of parameters we have are sort of compressing the information about the state space. But given a state, we can still use the function to compute its value. And then that's how we were doing policy improvement. One way or another, we were trying to do all the same things, but with these approximations. And one comment early in part 2 is that actually, like the policy improvement theorem that here, this is like just a summary of the policy improvement theorem, but the whole mechanism of this, it doesn't actually work in the case of approximation. Like we've been using it, it often does work, but there's no like theoretical guarantee that this method of policy improvement works when we're dealing with parameters and approximation. So in chapter 13, we're going to introduce this entirely new method, which doesn't rely on policy improvement in this way. And instead, it's an attempt to directly create a policy function where like we are just trying to directly optimize the policy without first going through the value function. Whereas in all these tabular methods, we use the value function as a stepping stone to compute the policy. Like in this way, this is just showing one way in which it works. It's like once you have a value function like this, you can just take the argmax of it, basically whichever action is the most favorable at this state. Okay, so that's like why like what we're doing now is distinct from all of the previous techniques. So are there any questions about this, like policy improvement and how what we're doing now is different? Okay, so I'll move on to what we're actually going to get to in this chapter, which is so now like this policy pi has some set of parameters theta, and these parameters, like if it's a case of linear approximation, this will be some vector that matches the size of the state space, or it matches the size of how we're encoding the state space or the state action space. But the policy function just tells you, given a state action pair, what is the probability of taking that action? Now, like here, the way it's written and what will continue on in this chapter is that like the state action pair is sort of taken as a combined input to the policy function. But of course, like this is supposed to be a probability distribution. So, really what it should be more accurately, or what I find is a more convenient way to define it, is that you have this policy function which gives you the vector of the action probabilities for a given state. So like that way, like the actual output, because like all of the probabilities across the actions will have to sum to 1. And we're going to mostly deal with discrete action spaces where there aren't too many actions. So, I guess like there's another case later on of continuous action spaces where you can no longer do that, in the same way. But I mean, still like your function can still output the distribution over actions. Here, the way it's defined is the function is actually outputting a single probability value, but you do have to make sure that, if you consider all the actions for a given state, that these end up summing to 1, or, it's not actually a proper probability distribution. So, then the idea is that we're going to try to directly optimize the policy with some gradient or some form of stochastic gradient descent if we can actually take samples from the environment. And in order to do that, we need to compute a gradient of some performance metric that operates, that is some function of the parameter space. Now, the performance metric we're going to use is something which we have already defined and we're familiar with in part 1 of the book, and that is, actually, do they not even define it until later? Okay, maybe it's mentioned later in the book, but this performance metric is going to actually, it's going to be related to the value function, but it's going to basically be what we expect the value of the starting state to be, where like the starting state is whatever state we expect the environment to start in. And so we're still like trying to do the same thing where we will end up finding the hopefully finding the optimal value function, the value function with the highest values, at least at the starting state. But we're going to go about it in a completely different way. And, like before we actually get into it, it's helpful to go through some of these definitions of what we're going to do. And in order to apply these techniques, we're going to have to define, here like pi is going to be the policy function we're using. And we're going to end up having to take like the gradient of pi with respect to the parameters data. So this technique will work for any function we write down for which this is possible and for which we can, use it to compute these, these policy probabilities for every state. Now, because this has to be a probability distribution, it's useful to only consider this particular case of how the function is going to work. And that is that instead of just jumping straight to pi, we're going to consider this function h. And what h is going to do is just produce some numerical value for the state action pair. And this numerical value is, we're going to refer to it as like a preference value, but it could be any real number. And what's useful about this is that, that way our function is not restricted in any way. Like we're not going to run into a problem if the function outputs, a number greater than 1 or a negative number, because we're just going to define the policy function as something that takes the softmax of this preference function. Now, we had discussed the softmax in chapter 2 of the book when we talked about the gradient bandit. Sorry, this is the notebook from part 2. I think in here I had here. So this is like a visualization of how the softmax works if you're not familiar with it, but it really is a function defined on a vector, because you can see like the way this is written down, it's taking it is exponentiating the preference value, but then it's normalizing it by the preference value at the same state, but calculated at all of the other possible actions, right? So the initial exponential value is what forces it to be a positive value. And then, this denominator is what normalizes it so that it is a probability distribution. So you can see that in order to even calculate this, we do need to know like all of the other values that are going to appear in the denominator, which is why it's often helpful if this function will just, instead of defining it as individual values, just, spits out this preference vector, because we are going to need the entire vector to compute the softmax. And this is just showing an example of like, this is the simplest form of it. If you add this temperature term, which we're not going to end up using because the function that we optimize will sort of, it will be able to optimize it, with just setting this temperature term equal to 1. But, there's just this option of having a different term multiplied by every preference. But here, if I'll just set this beta parameter to 1, or yeah, close to 1. So then this is showing like an example of where the preference vector would output these like 29 different values. You could see they're all over, some of them are negative. And then this is the result of applying the softmax to that expression. So now all these are positive values and they all sum to 1. So this is like a true probability distribution. And you can see that like depending on it, if I change the number of items, it'll still work. And in this case, the number of items in the problem we're considering would be the number of actions that are available. So you can think we're going to have some function that's going to output these preference values, one for each action, given some state. And then we're going to convert it to this probability distribution. So any questions about how the softmax works? Good. But yeah, I mean, this is also commonly used in like classification problems, or even like LLMs, where you're like predicting a distribution over tokens, and whatever the output of the network is, you would apply the softmax to it to convert it into probabilities. So then, going back to the simplest form of a function approximation that we were using, which was linear approximation, we had previously considered this case where we take all the state action pairs and we create some function x, where the function is going to map the state action pairs to some vector of a fixed size. So here, like d prime is the size of the vector here. And then when we compute the preference value, all it is just the inner product of the parameter vector with whatever the feature vector is for that state action pair. So, right, like this is just a dot product. And then to get all these values here, you would basically have to take, whatever the state is, you'd have to go through all of the actions, map each of them to a new feature vector, right? And then take the dot product of that in order to get all of these preference values. There is, let's see, and there's also a discussion here of the advantages of this method. I mean, one, I already mentioned the fact that the policy improvement theorem like doesn't even work in theory for function approximation. So we'll see that we actually have like a theorem in this case that actually does have some guarantee of improvement for the policy. But another thing that might be advantageous is that doing this process will not actually require calculating the value function. And it's possible that it's actually easier to calculate a function that is an optimal policy than it is to actually calculate like an accurate value function. So that way we can like shortcut the process of needing a value function. And it might not need to be as complex either with as many parameters. Another advantage is that these preferences can be any value. And you can see here, like when we take the softmax, the optimization process will drive these preferences up and down, but there's nothing that requires this to become a deterministic function. Like here, you can see like if you have these, any finite value for the preferences, you end up with, in general, like non-zero probabilities for multiple actions. And there could be some cases, which we'll see an example near the beginning of this chapter, where you actually want a stochastic policy, and the optimal policy is something stochastic. I mean, that will generally only happen in the case of function approximation where we don't necessarily know the exact state we're in, but that's also the case that we are most concerned about in this chapter. Now, I had mentioned this other way of doing this, of parameterizing this, which I think is a little more convenient. And I see here, right? I'm just going to refresh this notebook because I think some of the LaTeX isn't rendering perfectly. Oh, sorry. Take a few seconds to refresh this. Okay, so I mentioned this alternative way of doing this, which is that instead of thinking of this as a function that outputs a single value, we can think of it instead as a vector function. So I'm going to say that, like, let's say we have an environment where there's NA actions. Okay, this is like total number of actions like available in the environment. And then this function is going to operate on a state, and it depends on the parameters theta. And this is a vector function, and it's going to output a vector of size NA, one value for each action. And we can also write it like this with these subscripts, H1 all the way to HNA. And these will be the action preferences at each state. Now, if you do things this way, then the feature vector you're going to create only has to depend on the state, right, rather than the state action pair. So now I'm going to encode, these states into some vector of dimension D. Okay, or now D is just some choice that you make in how complicated, how many parameters. I mean, we'll see it in the case of linear approximation. This will have to match the number, this will scale with a number of parameters. There are, in nonlinear approximation, you can just choose this independently from the number of parameters, right? But you have to do like select some function that's going to map the states to this feature vector. So then, since everything's operating on vectors here, I'm going to define this new notation for the softmax just to make things easier. And here I'm going to define it as a function that operates on some vector x. And I'm going to also use this notation where if I exponentiate a vector, it just means that I'm taking the individual components of it and taking the exponent of that. So that way, I can use this symbol sigma to just denote the softmax applied to a vector. And then, this is just a short way of writing what that is. But this expression contains, all of the components of the softmax. So, then also our function, now our policy function is also going to operate on the state and using the parameters theta. And it is just going to be the softmax applied to the preference vector function. And now in this case, because we need to output a vector, our parameters are going to be most easily written down as a parameter matrix where they have D rows and NA columns. But basically, whatever dimension we've selected for the length of the state feature vector, that'll be the number of rows of the matrix. And then we'll have a different column for every distinct action. But effectively, what we're doing here is that instead of having a mapping for all the state action pairs, for this linear function, we sort of have a separate set of parameters for each action for a given state, because they're going to be separated into the columns of this matrix. And then when we compute this preference vector, it is just a matrix vector multiplication, right? Where this will, then produce a vector of size NA, where this is the number of actions. And then, I'm also going to use this convention where if I have a vector, just the subscript means that you're going to take, the ith component of it, which I could also write, without the bold vector notation. Okay, so are there any questions about the two different ways of doing the parameterization? So I had mentioned that in order to do this, we're going to eventually have to take the gradient of the policy function. And just to get, some things out of the way early on, actually, I should make this a little bigger. We might as well see how to calculate all these gradients just in general for the softmax function, which will end up coming in handy later. So actually here, I'm gonna do it in both cases. Actually, what I've written down here, um, I'm going to consider the case of the preference function being this vector output. But here, what this expression means is that we have the softmax of the vector output. And when we take the gradient, right, like the gradient itself is a vector because the gradient we're considering here is the partial derivative of the function with respect to all of the parameters, right? But, to take this gradient, like the actual function that we're taking the gradient of should be just a single numerical output, not the vector function. So what we really care about is the gradient of this vector function, but only at a particular index. And here the index we care about is the index of a particular action. So, here I'm just writing it down as the preference vector and the softmax function. And here I'm just using that notation of how the softmax works, where the numerator now is only this single component of H, right? And the denominator is still including the sum over all of them. And then in order to calculate this, here what I'm writing down is an expression for each of the components of the gradient, right? So this gradient is going to have one component per parameter, right? So here, this is like each component is just the partial derivative of the softmax function with respect to theta at a particular index. So then the rest of this derivation is just applying the chain rule to this repeatedly in different ways and rearranging some terms. But this is just the quotient rule first. So here this is like the 1 over v squared term of the quotient rule. And then this is we have like vu prime minus u v prime, and the chain rule here is just being applied to each of these exponential components. But we end up with this common term, right? The e to the h at sub a, where a is the desired is the action index that we care about. So we can factor that out. And then there's this little trick in this derivation where you can see this squared term, I'm actually going to split it in half. So I'm going to take the first part of it, one of these, and I'm going to combine it with this exponential term. And the reason for that is that this expression here is just the original expression for the policy function, right? Like here, you can see it here. This is the policy function. Like this is the softmax taken at component A of the preferences. So this simplifies to just that softmax. And then I can distribute this inside of here where, these indices are different right now. This is like a sum over L because I'm already using K inside of here, but, these indices are arbitrary. So I'm just taking the other part of the square here and combining it with each of the terms inside of the sum. And that way, each of these terms in the sum also reduces back to the policy function. Now, another thing that happens that simplifies this greatly is that this part of the sum is just the sum of the policy function over all of the indices. And here that I'm omitting s and theta in these expressions. So this is the policy function at a particular state. But this sum, like this is just the sum of a probability distribution, which is just 1. So this goes away completely. And what we're left with is just this expression that involves the partial derivatives of the preferences with respect to the parameters and the actual, policy function itself. Now, this applies in general, like it doesn't matter what h is, but we can now consider, what does this expression look like if we have the linear case, where now the preference function at h is just this dot product, like I mentioned before. Now, all we need to calculate is the partial derivatives of this. And it should be obvious from this dot product that, this is just, right, a sum of the components of x multiplied by the components of theta. So then the partial derivative of this with respect to the ith component of theta is just going to be the ith component of the feature vector, right? All the other terms cancel out to 0. So if we plug that in, we notice that this first term in the sum, all we have to do is replace this partial derivative with that particular component of the feature vector, right? And the component depends on the index of theta in the denominator, which is, which component of theta we're taking the partial derivative with. So here, like the expression, like the only partial derivatives, and we saw this before with linear approximation, that the only thing in the linear case, the only derivative you have to worry about, it all simplifies to just knowing what the feature vectors are. And then under this is just is the other case I mentioned, where now theta is this parameter matrix, right, instead of the vector. So here, right, I have the feature vector in terms of both the state and the action. And here I have the case where the preferences, like I still have this component of the preference vector, but it's the result of this matrix vector multiplication. And then, you can, because theta is being indexed by two different indices as a matrix, it's also convenient to just index the gradient with the same two indices, because the only thing the gradient's doing is making sure we take a partial derivative for every component of theta. And here the components of theta, just for convenience, I'm just indexing them as I and j, right? So now, if you look at how this matrix multiplication works, the partial derivative now is a little different. Here, it was just always the feature vector component. Now here, we have these two different components to worry about, and we only have the state feature vector, but this partial derivative now is just the state feature vector at the column that corresponds to the action that we're talking about. So that's the value in that column. But then, right, this is if j is the column index of theta, and then in every other column, this partial derivative is 0. So it's a more sparse partial derivative than this one, because right here we have, like, there's a dependency. The added complexity here is in the mapping of the feature vector. So then if we apply that to here, right, this is like now this piecewise, like, conditional expression. And just going back to this original term here, what ends up happening when we compute this is this sum ends up getting reduced to a single component, right? Because here, this is only non-zero when the second index at the bottom here is equal to the numerator index, right? So here, this is now going to be the partial derivative with respect to I and j. Now, this sum is only going to matter when k is equal to j, which we see here. So this sum gets reduced to this when k is j. And then also, these partial derivatives end up being 0 for some of the components as well, right? So this term is only going to be non-zero when j is equal to a, right? So we have this part of the expression for all of the terms in theta. And then this part of the expression only applies to that one column when j equals a. So, right, this is just one expression here. This, we have to worry about which column we're in of theta. But, that's why it's convenient to write data with these two different indices here. Because that's the most natural thing we're keeping track of, because these indices end up separating the parameters in columns that correspond to each action. Okay, so there's just a little bit of calculus and algebra, but we're going to end up using both of these expressions later. And then this is the general expression for the gradient, where there's no restriction on the function that calculates h here. So any questions so far about this, computing the gradient of the softmax? Okay, so we can move on to this example in the book. So the first example in this chapter is this corridor grid world. And the purpose of this example is to show a case where you would actually want a stochastic policy instead of a deterministic policy. So this little diagram here shows how this environment works. Now, and this is very representative of like what happens when you do function approximation on problems. I mean, here we actually know what the full problem is and how it works. So the true problem has three different states and a terminal state. And there's two actions in the problem. There's the left action and the right action. And episodes always start in this state number 1 here, and they end when you reach the goal state. Now, trivial, like this would normally be a trivial problem where you would just take the right action 3 times and you would end up at the goal. But now this middle state, the actions are reversed. So they have the opposite effect. So attempting to go right will send you left, and attempting to go left will send you right. So now, let's say we actually knew what states we were in. If we were in the state, then the problem would still be trivial, right? Because we would just go right in the first state, then we would go left in the second state, which would bring us to the third state, and then we go right again to the goal state. But the point of this example is that the way we're doing the function approximation obscures what state we're in. So from the perspective of the function, there is only one non-terminal state. So now we can identify what action we're taking, but the policy function is basically only able to output a single distribution, right? Because all three of these states will end up getting mapped to the same action probabilities. And here, the way they're showing it is when we map this mapping function, it does distinguish the right and left action as these two separate one-hot vectors, but there's no difference in how the mapping works depending on what state we're in. Okay, so does that make sense to everyone?
Yeah, that makes sense, that the mapping is just the action states, which there's only two of them, either go left or right.
Yeah. So here I have this implementation of this. I'll probably end up redoing this in some way, but this set of functions is able to simulate this environment. Now, what this is showing is if you have a random policy where there's this what this means is just there's an equal probability of taking the left or right action. This is showing an episode that was taken, which actions were taken. This environment gets a reward of -1 for every step. So the final, and this is an undiscounted problem. So the sum of reward from the start will just be the number of steps that the episode took. And this is just showing, running this simulation. If you have the random policy, this was run, I guess, for 10,000 times. And the mean value is, about 11.9 steps. And this is for the random policy, right, where the probability of going left or right is equal at 0.5. So you could generate this curve in this way by, just doing random simulations and changing what this policy function is. But there is an exercise in the book which says, using your knowledge of the grid world and its dynamics, determine an exact symbolic expression for the optimal policy of selecting the right action. Okay, so even though the function approximation, can't distinguish between states, we can take this problem and say, well, what if you're restricted to policies where the policy cannot change from state to state? It can be a stochastic policy, though, but we can use our knowledge of the environment to calculate what the optimal policy would be. And this actually, what we're doing here analytically is what the goal of the policy gradient techniques are in this chapter, which is like, even though maybe you're restricted with this function approximation, is there still a way to optimize the policy? Here, we're going to compute it using actual knowledge of the environment and the probabilities. The technique, all these policy gradient techniques are going to accomplish this by sampling from the environment instead. But as a first step, we're going to try to do it analytically. And I guess I can start going through this, unless I assume no one actually did this exercise or has an answer they want to share. But if there is, please let me know. Otherwise, we can just go through it here. I'm gonna use some conventions here just to make it a little more compact, writing things down. So I'm just going to call P the probability of going left. Okay, and then the different state values, I'm just going to call V1, V2, and V3. Now, the first expressions I'm going to write down here are going to make use of, actually, I can go back here to the definition of the value functions. So notice that the state value function, there's this recursive expression for it where we can express the state value function in terms of the probability of taking each action, and then the probability of the reward and the value at the transition state. So I'm going to use this Bellman equation to, solve all the different values in this environment. So this first equation, this is saying that the value of state 1 is, now, if we go left from state 1, right, P is P left. So if we go left from state 1, then we just end up in state 1. Okay, so that's why there's a V1 repeated here. And then if we go right, we end up in state 2. So this is 1 minus P times V2. And then you get a reward of -1 for every step. So all these expressions are going to have this -1 and then the expected value of the transition state, right? We're here, these are the two possible transition states. Either we stay in state 1 or we end up in state 2. And then this is just, rearranging the expression a bit where, all the terms for V1 are on one side. And then, finally, this is like my final rewritten expression for V1. So we have an expression for the value of state 1 in terms of the value of state 2. Now, we can write down a new equation for the value of state 2, which is now, right, remember, in state 2, the actions are reversed, right? So if we go left, we end up in state 3. So that's here, P times V3. And then if we go right, we end up in state 1 again. So that's the 1 minus P times V1. And then finally, we have our expression for state 3. If we go right, the value of the terminal state is defined as 0. And then if we go left, we end up in state 2 again, which is this p times v2 minus 1. So, we can then substitute this expression for v3 into equation 2, right? So now we have, if we do that, then we get rid of the dependence of v2 on v3 in this expression. And if we collect some terms, we can end up getting an expression, this expression for v2 in terms of, wait, there should be a v, sorry, this should be v1 actually in this expression, but this is an expression for v2 in terms of v1. And I think or no, maybe I just replaced it. Yeah, so I think, so here in this step, right, we have an expression here for v2 in terms of v1. Now, this equation 1 prime already, we can completely replace our expression for v1 in terms of, v2 minus 1 over 1 minus p, right? So that's what appears here, right? We have v2 times 1 minus p, and then the 1 minus p in the denominator cancels out this term. And then, the rest of this is just algebraic simplification, right? But you end up finally with this expression for v2, only in terms of p, right? So here I've already replaced the v1 with v2. This is just a matter of collecting terms and isolating v2. Then, we can go back, plug this expression for v2 into v1, simplify it, and similarly for v3, we have our exact expression for v2. We can plug into v3. So to summarize the state values, this is what they are. That's what this curve here is actually showing v1 as a function of p. Although here this is actually p left. Here this is p right. But I have the plot here. Now, this plot, this is only showing the state values for the starting state, which is v1. Here I'm showing the state value for all 3 states, right? So the bottom curve is v1, which has the lowest values, which makes sense. It's the farthest away from the goal. This is the value of v2. And then this is v3, which has the highest values because it's closest to the goal, right? But this is showing, the probability of the right action and the state value you expect for each one. Now, but the question was, what is the optimal p-value? So we have this expression for v1, and we'd like to find the value of p, which maximizes it. So we're just going to do the typical thing of calculating the derivative with respect to p, and then setting that equal to 0. It ends up being a quadratic equation. You can see this denominator term causes problems when p is either 0 or 1, which, luckily, so the answer we're going to get is not going to be p is 0 or 1. So we can safely ignore this denominator term, which is going to, cancel out when we set this expression equal to 0. And then we just get this simple quadratic equation for p. We can just solve it, and we get p is about, well, it's root 2 minus 1, but it's 0.41421. Remember, that was p left. So we have p left is about 0.414, p right is 0.586. And we can also plug this p right into our formula for v1. And we find that the value is, about negative 11.65, which is the number of steps we would expect if we use this optimal value of p, right? So that's what's being shown here. P right is, close to 60% of the time. And, also it's worth pointing out in this example, because of this switch, right? Obviously, any deterministic policy fails for this example, right? Like you can see in this curve, the value goes to negative infinity when p is either 0 or 1. And that's because you'll just keep getting stuck right? Whichever. I mean, the only place a deterministic policy is successful is if you started in this state every time, which you can see here, this value approaches 1 as the probability of right approaches 1. And that's because, here, if we go right, we actually reach the goal. But in the other two states, it doesn't work. And we've already defined the problem is we're always starting in this state. Now, the exercise doesn't ask you to do this, but you can also repeat this process for state 2. It's just, we just end up differentiating the expression for state 2. And if we do that and solve the quadratic equation, we end up getting P is a slightly higher value of around 0.45. And then P right is a slightly lower value, 0.55. So, right, this doesn't actually match the result we got for the first one. And you can see with these curves, like the optimal policy if we start in V3 is to go right. The optimal policy if we start in V2 is actually to go right slightly less often than if we had started in V1, right? Because in V1, it's close to 60% is where the optimum is. And starting in V2, it's actually closer to like 55%. So that, I don't know how much intuitive sense that makes. I mean, it should be obvious that starting in this state, the optimal policy is totally different. But, from here to here, I guess, yeah, it makes some amount of sense. But it depends on the distribution of when you expect to end up in states. But it's basically saying that, right, remember, this is the switch state. So if you start in state 2, it is favoring to slightly more often than in here, actually try to go left, right? Like P left is higher than it was here because, at least if we go P left here, we end up here. And then, obviously being in this state, favoring P left less often is better. But probably the difference is because of this asymmetry where from state 1, right, if we go left, we don't actually have any downside to going left in this state. I mean, like we don't get further away from the goal for going left. Whereas here, if we end up going here, we do get further away from the goal because there's this sort of artificial wall here which prevents us from going. Yeah, but the actual process of doing this derivation is just writing down the Bellman equations for the value function and then solving it. It happens to just result in a quadratic equation that you can solve for the optimal value. But any question about this example or the different optimal policies depending on what state you're starting in? The point of this example is that, under this sort of restriction of having a single policy at every state, the optimal policy is something stochastic, not deterministic. But you can think of this little corridor as a subset of a larger problem where, in general, like our function's not going to be able to distinguish every state. So you can think of some small set of states as being indistinguishable and having some dynamics like this where then, that there is a reason for having a type of policy optimization where we can have a stochastic policy, right? But again, this only comes up in function approximation where if we could actually distinguish these states from each other, we wouldn't need to have a stochastic policy. But yeah,
Yeah, that makes sense. Thanks, Jason.
Okay. So the next, section covers the policy gradient theorem, which is, you could argue, the most important part of the chapter, because it actually creates the theory of how we sort of do what I did in this example, but actually for a problem where we can't write down all of those algebraic expressions. But I'm first just going to state, what the policy gradient theorem provides, and then there is this, of course, this box in the book that proves it. I have, I think I tried to elaborate on the proof a little bit so it's a little more clear what's happening, but we'll see if it actually is, if there's any questions. But going back to the original task, which is we want to try to do some kind of parameter update where we're going to take gradient steps where the gradient is, the gradient of some performance metric, which is a function of the parameters, because the parameters affect the policy. And the performance metric we're going to use is the value at the starting state. And this derivation is for an episodic problem where we always start in a particular state. But this also generalizes to a distribution of starting states and eventually to continuing problems. But for now, it's simpler to do this derivation just worrying about this one starting state. And this is the final expression we're going to use of the policy gradient theorem, which is that the gradient of this performance metric, where here, the gradient are the partial derivatives with respect to the parameters, we can write down as the sum. Now this, again, this is the on-policy distribution, these mu's. So mu sub s is the probability of being in state S at any given time in an episode. So, this ends up, this can be reduced to an expected value because, this is some distribution that we can observe from the environment. And then we have this sum over actions of the state action value times the gradient of the policy. Now, we'll see later that even though it looks like we need a value approximation here, we can also replace this with a sample, at least in the Monte Carlo case. And then this gradient is something we can compute because this is the gradient of the policy function, right? So the whole goal of the policy gradient theorem is to derive an expression that we can, first of all, that we can sample from, like, we can sample something that is an unbiased estimate of whatever the expression is, and also that's only in terms of the gradient of the policy function, right? Because the policy function is really what we care about. And that's also the only thing that really depends on the parameters, is the policy function. So that's what it shows. Now, in terms of proving this, there's sort of two main parts of the proof. And the first section of the proof involves just coming up with a more convenient expression for the gradient of the value function just at any arbitrary state. And actually, another thing that's helpful to keep in mind was from chapter 1. Oh, sorry, this is 13 again. From the first part of the book, the different expressions for the value functions, right? So here, for the gradient, we're going to derive it from the gradient of the value function here. So remember, the value function, it's defined as the expected value of the discounted return starting at a given state. And then, this is just expanding, like the definition of the expected value. This is the expectation under the policy. And, because here we now separated these different actions, right? We ended up writing this as an expected value, or rewriting the expected value with the probabilities of the policy. But now we can actually take the action separately. And remember that this expectation where we had specified the action was the definition of Q, where Q was the state action value as opposed to just the state value. And then we also had this expression for Q in terms of V, where this is just using the Bellman equation again, where we're now using this probability transition function of the environment. And this is just a way where, like, this was important in part 1 of the book, where if you have this transition function, you can always compute the state action values from the state values. And that's what's being done here, right? And then similarly, we have multiple expressions for Q here, but we're going to end up using this in the theorem proof. So just keep this in mind, these definitions of the value function. So here, again, right, this is like going back to part 1, that's this term, right, where we express the value function in terms of this sum of the action value function. So that's what's being done here. Okay, and then this gradient, we just distribute it. We use the product rule to split this into 2 different terms. So now this first term is unchanged. In this next step, you take now we have, one of these terms is the gradient of Q. And then we're going to replace Q with that expression where we derive the action values from the state action values. Now, part of this sum, right, like this is a sum over both S prime and R. But if you look at the first part of this sum, right, this has the probability function and has R, but the gradient here is in terms of the parameters theta, right? So this piece of the sum is actually independent of theta. And then this second part of the term, we can actually, get rid of this sum over the rewards, because we already had this expression, right? If we take this function and sum over R, this is just part of the definition of the probability transition function, is we end up collapsing it, where now this just means the probability of transitioning to state S prime after, taking action A from state S. So, because the sum over all the rewards, they all have a probability of 1. So, fine. Now we have, this expression, but notice that this final term in the expression, right? This is just the original thing we were calculating, but evaluated at state S prime instead of state S. Right? So now this has turned into a recursive expression of sorts. And that's the next step here, is expanding this expression. So it's all the same, but now I'm going to take this entire expression. I'm going to sort of increase the state index, if you like, by 1, where now all of the S's are going to become S prime. All of the S primes are going to become S double prime. And then that is what is right here. This sum term is just this entire expression where that transformation on the states occurs. Okay. And actually, I think part of this is still cut off. Yeah, so we did so now the recursive expansion has been done once. And the next step is to try to separate the terms a little bit, right? So inside of this sum here, we can treat these sum terms separately. So here, this first expression is just the gradient of the policy times the action value at SA. And then the second term, right, like we still have the sum over A on the outside, but the second term, like we still have this same looking expression, but now instead of S and A, it is S prime and A prime. And there are these extra sum terms at the beginning. And then, of course, here, this expression is different because now this expression still has the gradient of V left over, whereas these we've, through the recursion, we've eliminated the gradient at V. But the point is, since we have this recursive expression, we can repeat that process again. And you notice there's this pattern here. I just continued the pattern one more step here, where you can see that we just keep adding these terms where we sum over the actions times the policy at the actions. Then we sum over all the transition states times the probability of the transition states. And here, after one step of that, we then multiplied it by this expression in terms of the gradient of the policy. Here, we just extended an extra step. Right here, we have now another sum over the policy at the actions and another sum over the states, where here I have to increase the index again to S double prime. And this process can just be expanded indefinitely, right? Now, the question is going to be, how do we interpret all of these terms? And to make it a little easier to write things down, I'm going to take this expression, which is the one we really care about, because this is the expression that has the gradient of the policy. And right, this is a sum over A. Like we're just summing over all the actions regardless. So this is really just a function of S, right? So like S is because like we actually sum over A, the index of A is irrelevant. So I'm just going to write something new where I have this new expression, F of S is just this sum term where we sum over the actions and we take the gradient of the policy function for that action at state S times the action value of that action at state S. So if we do that, we see, the first term here is just F sub S. Now, the second term, right, here I'm just writing it a little more compactly. But if you look at what these sums are, right, we're summing over all the actions times the probability of the action, and then we're summing over all of the transition states and the probability of ending up in the transition state after taking action A. And what this expression really is the sum over all of the transition states of the probability of ending up in state S prime taking one forward step. And that's what's being shown here, right? This one means we're going from S to S prime in one step under the policy pi. And that's what all these sums of probabilities are computing, right? And then the F term now, we have the sum over all these transition states, is S prime. And then if we extend this process to the third term, right? This is the third term written out. This is the original third term in the sum. This last part is what I'm going to replace with F, right? Where now it's S double prime. And now we have these four different sums, or we sum over actions, transition states, transition actions, and then second transition states. But again, what this really means is that we want to sum over, again, all of the possible S double prime. Now, in general, also, this, the prime on this sum here, this is just to distinguish it from the other sum. But once we get an expression like this, assuming that there's some non-zero probability of reaching, any state, I mean, even if there's zero, we can still add them with zero probability. You can just think of this as a sum over all of the states. The ones we can't reach will have a probability of zero. But it's just a sum over the states of this f expression at each state times the probability of transitioning to that state after now 2 steps instead of 1 step. And if we extend this process out, every term just looks like this, where, I mean, I didn't include the first term, but the first term is just this after 0 steps, right? And of course, the probability of that is just 1. And there's only 1 state we're actually in, which is this S, which is the state we started in. So if we keep, extending this process, every term is just the sum over the states. So here I'm just replacing this index thing with, let's just sum over all the states in the state space. That's this X is just all the possible states. And then it's the probability of transitioning from the starting state into X after K steps. And then we would evaluate F at X, whatever that transition state is. And this sum, so this is each individual term is K. And this whole gradient expression is all of those terms summed up. And K in theory could go to infinity, or it would be the maximum length that an episode could be under the policy. So now we can return to the expression we actually wanted to calculate. I see here one of these things should be fixed. But so here now I'm replacing S with S naught because that's like the starting state that we actually care about. And now this is just showing the sum of all the terms, right? Where now I'm including all of the K's here, right? Because this is for like a K of 2. So this just means I'm adding up all these F terms at all these possible states S times the probability of transitioning from the original state S naught to the state S in K steps. Now this here, I wanted to just so we start in state S naught, right? And then with the policy, like this is showing like all these different actions that we could take. And then additionally, like each of these actions with the environment will then branch into all these new states, right? So these are all different potential, S states. And then this would be like 1 step. Okay, so I've sort of omitted what happens here, but you could imagine this row covering like the entire state space. And then we have this probability, right, of going from S naught to S in K steps under the policy. But this probability value is going to tell you like after 1 step, like here, this is after 1 step. For any state in the state space, what is the probability that we could be in that state? And then as you increase K, you just expand this chain down to like new sets of states. But this term here, right? So we end up having this expression, which is the sum over K of the probability of going from S naught to S in K steps under the policy. And what this is really saying is, what is the probability of going from S naught to S after 1 step, 2 steps, 3 steps, multiple steps, but it's really like, you could also think of it as the sum over like cases of like being in S, right? Like, or this is like really should be the probability that you're in state S, and all the different ways in which you could be in state S, right? Because these Ks, after one step, two steps, we're just covering all the different ways, circumstances in which you could be in state S. And, we're multiplying this by 1 per state. But, this also you can think of as just an expected value, where now this is like the expected visits to state S, or like the expected number of times we find ourselves in state S. Because remember, we're weighting all these cases by 1, where 1 is like, that's like counting as 1 visit to state S. So we just have like if we have these different transition probabilities, chains of this, where I'm just saying like, so here, like we end up in state S after some number of steps, and then this is like the case, and we just expand this to all of the cases, right, and weight them by 1. So that's why in this expression here, that's what this term N or eta S is, just the expected visits to this state S. And, so we're weighting every visit by 1, and then we're summing over the probabilities of, basically all the different ways that we could make a visit to state S. So we had used this before when we were calculating these on-policy distributions. Now, here, this is just a little bit of like algebraic trickery to get a nicer form of this expression. But here, I'm just multiplying this by 1, where 1, right, like this is just multiplying and dividing by the same thing. Now, the purpose of this is to factor this term out, and then use this expression. Now, what this is doing is it's taking the expected visits to a state and normalizing it by the total number of visits to every state. But this expression is just the on-policy distribution, right? And then this expression is just the denominator term, which is really, I believe, like this is just sort of the expected length of an episode, which is just some constant term, which doesn't matter. Yeah, like it doesn't actually, this can be compensated for by like the learning rate in the gradient, right? But the point is like, this doesn't actually depend on the state we're in. This does. So now what we have is something that is proportional to the sum of the on-policy distribution of this term F, right? And this is the term that has the gradient with respect to the policy function. And then we can also just rewrite this as an expected value, where now I'm replacing F with the original term that F represents. But, right, this is the on-policy distribution. So this expression here is just the expected value under the policy of F. Now, we can actually sample this from the environment, as long as we have some unbiased estimate of Q here, which we can get if we collect a full trajectory through the environment. Then, this expected value, we can sample from it as long as we are collecting data from the policy, right? Because if we follow the policy, we will end up collecting data according to the on-policy distribution. Right, so we apparently have arrived at something that we have a chance of using, and the easiest way to use this is this reinforce algorithm, which is a Monte Carlo algorithm, and it's the first one we're going to consider. And the reason why it has to be a Monte Carlo algorithm is because in order to have an unbiased estimate of this that doesn't depend on anything else like a value estimate, we have to have an episodic problem where we collect the episode all the way to termination. And that is what we saw. Well, if you go back here, right? Like previously, if we actually have this episode trajectory determination, then we can directly compute this value of G, right? Because the definition of G is something that actually is the sum of rewards all the way to termination. And of course, V is the expected value of G, right? Q, this is the expected value of G here. Now, G is something that we can collect from the environment, right? But only if we can actually take this sum to termination. So that's why the first algorithm here, reinforce, is a Monte Carlo algorithm. So we're going to start with this expression, right? So we have our gradient now is proportional to this expected value. And, to sort of massage this into something that we can sample, we're going to multiply and divide by the policy function here. Right? And now here, this is inside the expected value expression. So here we basically have, the expected value of this sum. But, if we're actually following the policy, right, like this also looks like the expected value under the policy because we're taking Q. So this whole thing inside the expected value, we can actually just replace it with Q at, an actual sample of the value function here, right, at S and A. And so now we've actually, gotten rid of this policy term. And then here we have the gradient, right, of the policy divided by the policy. And also, again, since this is inside the expected value, we can also replace the state action value sample with G, right? Because G, if we have this trajectory that we're sampling, right, we can just take note of the state action that was actually taken at time step t. And then we have the data of the trajectory looking forward. And that's what's going to give us the value G. So now we have something that we can entirely sample from the environment. All we have to do is collect, a Monte Carlo sample of a trajectory, go through it, and then at every state action pair, we have our sample value of G, and then we have to be, and then we just compute the gradient of the policy function here. And, this expression, this gradient expression is also called the eligibility vector, and we can also write it more compactly as the gradient of the natural log of the policy function. But, if you evaluate this analytically, this just expands to this. But you'll see in most of the pseudocode, the way this expression is written out is it actually uses the eligibility vector here, A. Now, this is the case where our policy function, right, computes like a single value for the state action pair. Alternatively, I mentioned we can also have our vector policy function where we output a vector of probabilities for a given state. And then in that case, the thing we want to compute is the gradient of the natural log of that, but taken at the index for the action at time t. So then, sorry, if we go back to the book. So the book has pseudocode for this reinforced algorithm, but the basis of it is just using this gradient expression, taking the thing inside the expected value, treating that as something that we can sample. And then, so this is the whole thing that we can sample. And then this alpha is just a step size parameter. And we're just going to update the parameters at every step of an episode. And here is the pseudo, it's very short pseudocode, but because it's a Monte Carlo algorithm, but we're just going to go through the episode. And so we have this trajectory of states and actions. Here they're going through it forwards. You could also loop through it backwards, but here they're just computing, right? This is the discounted return looking forward through the episode. And then that's just being multiplied by the gradient of the eligibility vector, or sorry, the eligibility vector is the gradient, but it's just G times the eligibility vector. And that's what's going to do the gradient update. Now this graph is showing applying this algorithm to the corridor grid world, right? This is the example where we had already computed the optimal value of P here. And at that value of P, right, we should get a value of about like negative 11.65. So here, this is, of course, this is noisy because this is actually showing collected samples during the training process. But for different learning rates, this is showing that as long as the learning rate is sufficiently small, like here, this does appear, to approach the optimal solution. So this is working, at least on this example. And the way this was done is, this was actually run with this type of a feature vector mapping, where the feature vector mapping hides what state we're in, right? Which is why, we can't just have an optimal policy outright. We can only have, this is the best that we can do is this optimal stochastic policy. But, the simplest version of a policy gradient algorithm reinforce at least verifies that we can approach this optimal solution for this example. And the way it was solved was also with linear approximation. And another just, quick thing that we can end with is how do you actually compute this eligibility vector, right? This thing, which is the gradient of the log of the policy under different, common circumstances. And one common circumstance, sorry, so this, I have this implemented to in here, but this is just showing the same sort of graph with different values of alpha. Now, this exercise, the final exercise in this section, is just asking you to get an expression for the eligibility vector under different like linear feature vectors. So here we have the case where we have linear approximation, and again, all the action preferences are just the dot product of the parameter vector with the feature vector of the state action pair. Now, we had already derived the expression above. It's what I showed, early on for the actual, gradient of this linear expression for the policy function. So this was the gradient we had. And you'll see that for the eligibility vector, all we have to do, like if you take the gradient of the log of a function, right, it's just the gradient of that function divided by the function itself. And you can also break this down on a component by component basis. But if we apply it to this case, all we do is divide by like pi underscore a, which is just the policy value at action A. And then we have this simple expression for the eligibility vector in the linear case, here, this is what we're supposed to verify in the exercise. And this is just the component, the per component version of the equation. And so this is a vector equation. And this is just these little indices are just showing, for index I, what you do. And similarly, you can apply the same thing to this, alternative form of the parameters, where now we have x just of s, just the state feature vector. And this is the expression that we derived with now two indices for rows and columns of the gradient. Where now there's a difference between the column that corresponds to the action we care about and the other columns. But, this pi sub a, this is the thing we're going to divide out. So for the eligibility vector, it just simplifies to, this case expression in here, where we get rid of pi a. But yeah, they do look very similar in the sense that they both, only depend on pi, like the value of the policy function, and on the feature vector itself, evaluated like at each component. And then I already showed, yeah, so this is for the linear case. We have the general case from before. We're now like we still have the partial derivatives left in here. So remember, we already did it. We had this expression. It ends up being just as simple for the nonlinear case, where we now just divide this pi sub a away. And this is the expression for the eligibility vector for general function approximation. And finally, I just wanted to note this connection to the cross entropy loss. So if you're doing a classification problem and you have a function, you're trying to predict a class label. So let's say, your function returns the same sort of preference vector. So we have n classes. Our function returns preferences over the classes. And then to train this function, what you would do is have a data set where you have a desired output label for an example. And then we take the cross entropy loss of the desired output with the softmax of the function output. Now, this is the expression for the cross entropy loss between two distributions. So here, P is the desired distribution, and pi is the distribution that our function is putting out. And the cross entropy loss is just this negative sum of the desired probabilities and the natural log of the function output probabilities. Now, for most problems like this, the desired probability is just a one-hot vector, of the class label. So this will end up reducing to, you can actually just write this as a function of the class label and the output distribution, So all the terms in the sum disappear except one, and that is, for the index A, where A is the class label. So our loss function is just negative log of pi A. And then to do supervised learning with this, we would take the gradient of this loss function, and that's just the gradient of negative log of pi, But that's also the same exact thing we're using here for the eligibility vector. So if you have some function, that's designed to do supervised learning with the cross entropy loss of a function, you can actually use it to compute the eligibility vector, or it will be the negative eligibility vector, because there's no negative term here. Here, this cross entropy loss gradient has a negative sign. And the connection between the two is that instead of the class label being used, like if you have a data set, the class label ends up getting replaced, like here, with whatever action was taken in the trajectory that you have sampled with the Monte Carlo sampling. But in the end, it ends up being exactly the same gradient you have to calculate. And that's why if you do it in this way, this type of parameters, where we have like the vector version of this, where we're just mapping the state to a vector, and we have the parameter matrix, then that basically has a direct connection to doing like even linear classification, right, with supervised learning, where you would have a parameter matrix where the columns of the matrix would correspond to the different class labels. And then if you train it with cross entropy loss, it would end up being exactly the same gradient that you would use with stochastic gradient descent, where instead of looping through the examples and the class labels, you're looping through the trajectory and the actions. So yeah, that pretty much summarizes the simplest way that you can use policy gradient methods. And then the remainder of the chapter deals with basically ways of improving upon this, and also ways of dealing with this in the continuing case. Because again, all the Monte Carlo methods, they can only work for the episodic case. And this corridor example, this is an example of one where we would be unable to come up with the optimal policy with the methods we had previously used in the book, because all the previous methods would end up producing a deterministic policy. Or I mean, even if it's epsilon greedy, the epsilon is not really helping you much, because the policy is still mostly deterministic. And here the optimal policy is quite close to a completely random policy. Like the probability is around like 0.55, 0.6 for a particular action. And this policy gradient technique is the only method that can produce this type of stochastic policy. And even though this is just a toy example, it's important because often in real environments you have these sort of indistinguishable states where the optimal policy probably is some sort of stochastic policy, which you will be able to successfully find with this. Yeah, I think that was I don't think I had any more points on these first few sections. Yeah, I mean, this is useful too, because if you are adapting like a neural network algorithm to use with this, you shouldn't really have to change anything, because as long as you feed it data in this style and just treat it as a classification problem. So that's nice. Or if you have a linear like something that does logistic regression, it would be the same sort of thing. So yeah, are there any questions about this? I guess this whole final section of the calculating the eligibility vector. Because yeah, if not, I think we'll stop there for now, and then we'll see how far we get in the chapter the next time. But we basically have baseline methods and then actor critic methods after this.
Thanks, Jason.
Thanks.
Yeah, thanks, Jason. I might have to do a little bit of catching up, but this is important.
Yeah. Well, luckily, if you want to catch up on part 1 of the book, there are the individual chapters, but this summary notebook sort of puts all the definitions together, and yeah, it's probably worth going through because all these value function definitions are used in the policy gradient proof.
Can you put a link for the summary notebook?
Well, it should be, let's see, the link that Max posted.
Oh, is that the one?
Well, no. Well, that link has all of the export notebooks so far,
Mhm.
and this is one of those.
Oh, okay.
Let
Now
me
you-
see if I open the chat. But yeah, it should be possible to just here. Let me see. So here, okay. So here's the IO page. I think maybe this isn't. Oh yeah. So that was the repo page. Right. This is the IO page. There's a link from here to the repo page, but then this is the tabular methods overview export in there. But there's a table of contents on the IO page, so you can look at any of the notebooks. But yeah, this is just the static export of the thing I was showing,
Okay.
of the notebook I was showing. But yeah,
All right. Thank you.
and then yeah, I guess there's static exports through chapter 10 in here, but I'll add the others shortly. I just need to, or no, through chapter 11. Yeah, I just need to clean up the notebooks a bit and make sure that they render properly when you do the export. But yeah, I think that's good for now, and yeah, it sounds good to everyone. We'll just move on and finish with see how far we get in the rest of chapter 13 next time.